Afternoon or evening, depending on where you are in the world. It's nice to see the collection of excellent speakers brought to one forum. Today I'm going to talk about some more academically oriented research here than the previous talk, but certainly in line with the same types of applications where we've been exploring GaN HEMTs in power amplifiers above 100 gigahertz. Very complementary to the work that Professor Gray described earlier. I'll talk a little bit about the overview for what we need with heterogeneous devices and the demands for communications at higher frequencies. Some of our work is focused on circuit techniques rather than transistor technologies. So we call those circuit techniques embedding networks. And these embedding networks need to be provided to help boost the gain of GaN HEMTs at these higher frequencies. I'll show how these embedding networks have worked in some of the power amplifiers we've designed at 140 gigahertz. And then some of the work that we've more recently done has been on tackling the device modeling problem at higher frequencies and some of our perspectives on how you might use machine learning to improve your device modeling at bands where you might not have direct load pole information. So with that, I'd like to talk a little bit about the particular area constraints moving to higher frequencies. We've seen a lot of talks that focus on phased arrays. And so without jumping into a lot of phased array material, it's pretty clear as you go from a 5G frequency band at 28 gigahertz to a notional 6G or 7G band that might be a factor of 10 higher in frequency, there'll be a great amount of reduction in the pitch of a particular antenna element. So antennas get closer together. That means power amplifiers have to get smaller, and that means we need higher power density as we go up to higher frequencies to maintain a similar Pout. The higher power density must be also accompanied with high efficiency. Otherwise, we start to run into significant thermal flux issues. In other words, the amount of heat that's generated in a square millimeter obviously increases. Within the research literature, Huawei has captured this in a recent Journal of Microwaves article. The kind of way to look at the research literature and see this trend is comparing the frequency with the lambda over 2 pitch here. And as you can see in the recent literature, the red dots start to cross this line of lambda over 2 around 100 gigahertz. And so it's a fairly important research problem at this point to increase the amount of output power if we want to think about phased arrays or MIMO arrays or any kind of array at these higher frequency bands. At the same time, this points to higher power density, and that's something that we want to look at our portfolio of different technologies to address. And so when you look at comparing different types of material systems and the type of RF power that they can generate, the one way to think about this is to look at indium phosphide HBTs, silicon germanium HBTs, CMOS, and gallium nitride, and just basically consider what it takes to match to a particular load line, for instance, 50 ohms in these different technologies. And one of the things that, of course, pops out is that gallium nitride is always going to be able to deliver much higher power for a given load line. Or another way to think about this is if you have a fixed output power, what type of matching would you need to present to that device? And in this case, gallium nitride tends to provide a higher impedance, even if indium phosphide might be better matched to 50 ohms at a lower output power. So these load line conditions are very important once we start to look at how power amplifiers are going to perform at these higher frequency bands. And so a lot of this is probably well known to this audience, but to those of you who are gaining some experience with power amplifiers today, the power added efficiency is going to be a combination of factors, including the drain efficiency, which is related to how we bias the device and tune its output characteristic, the gain of the device, which will be characterized largely from Fmax of the technology, the device technology, and then a knee voltage and supply voltage. And this is one of the places where, of course, gallium nitride is going to be very valuable in terms of when comparing to CMOS. We get much larger swings relative to that knee voltage. And then finally, a feature of the back end of the line, the quality factor of the matching networks. Then this isn't such a big factor potentially at lower frequencies, but once we get to higher frequency bands, the losses of these matching elements and the types of matching elements we implement might start to introduce a PAE degradation. So when you look at when you look at the literature, and I apologize, this might be a couple years old, but when you look at the literature on PAE above 100 gigahertz, and you look at all these different device technologies, even though we've seen that the gallium nitride might have a relatively high power density, its PAE is relatively low compared to indium phosphide. Again, with the idea that that's probably because indium phosphide is a little easier to match to at lower power levels. So we'd like to bring up some of the gallium nitride work to make it more competitive with the PAE of indium phosphide, so that we might ultimately be able to get a better trade space between output power and PAE. We want to get the most out of a gallium nitride HEMT technology. The one we used in this particular work, and I'm using it throughout, so there's not a lot of jumping around of systems, is this HRL T3 process. The T3 process is not easy to use at 140 gigahertz. It has relatively low gain. And so there's an emphasis on low loss matching networks, and of course, ways that we might boost gain to make sure we get as much gain per stage, particularly if we have to make 20 dB gain in amplifiers. The number of stages is going to highly influence the PAE of the overall amplifier. So we want to stay away from large numbers of stages, also because it's challenging with the modeling accuracy we have to tune everything across multi-stages with a technology like this, multiple stages. So the T-gate process that you can see on the left, it's been reported extensively at this point by HRL, and it has an Fmax that in theory approaches 400 gigahertz. The device layout here for a 4 by 37.5 micron periphery is illustrated, and the notional results from a load pull on the device indicate at 140 it's capable of about 13.8% PAE at 23 dBm output power with this Z-opt condition. So given this device technology, we'd like to understand a little bit more about how we can best match the load line and get a gain match, and understand some of the performance limitations that are imposed by the back end of the line of the technology. This is a two metal layer process. In general, most people would think about this in terms of dividing it into matching at the input, matching at the output, and what are the lowest losses that might be possible for those input and output matching networks. But more generally, there might be better matching approaches that help us boost the gain of the device while simultaneously getting that load line matching and potentially even bandwidth from the transistor. So this leads us to our investigation on embedding approaches and embedding networks that could be used in these device technologies. An embedding network is basically a way of generalizing the two-port matching conditions that we are most intuitively familiar with into something that is a four-port network that could both incorporate feedback as well as those input and output matching networks. And so when you think about this generalization of a network that would be used to match to the device, you can think about adding to the left feedback elements between the gate and the drain, as well as series elements at the gate and the drain, which might be used for tuning, or series feedback as degeneration at the source of the transistor. But that's one simple way to think about it. If you go to the right, there might be other ways to incorporate feedback simultaneously between the gate, the drain, the gate, the source, the drain, the source. And this broadening of permutations on how feedback is introduced in the device becomes, at least to me, little non-intuitive. There's not a lot of easy insights that can be gathered from looking at a complex circuit and imagining all of the permutations of feedback. And so the embedding network is a way of capturing how this feedback might behave without worrying about the precise implementation of that feedback. We really want to get at this problem of how we might simultaneously get load line and gain matching for these higher frequency applications, as well as potentially introducing gain boosting. The idea of gain boosting here is to basically push the Gmax of the device above U. There's this essentially a few dB that we can get as we introduce feedback that might allow us to improve our gain in our amplifier. And the value of the embedding network is after losses to try to recover a couple dB of gain from the device. And to understand how this embedding might be used, we start with a very simple model that provides some intuition for people who might be familiar with how the feedback behaves in a couple situations, but then more generally consider the trade-offs between those different embedding networks. So the first examples will consider our source degeneration, inductive source degeneration, and capacitive neutralization, which are two very commonly understood approaches to gain boosting. In the context of inductive degeneration, what ends up happening with the GaN HEMT is that we can introduce a second spike in the gain in the Gmax response, and you see this when you look at the higher frequencies in green here. These are, for instance, a band of interest between 110 and 160 gigahertz. The black curves represents the Gmax when we have no inductive peaking. And when we compare that to introducing relatively small amounts of inductive peaking, 16 picohenries, 20 picohenries, 24, you can see what happens is there's a gain increase in the band of interest. It's relatively narrow band, but it can be useful if we're looking to improve gain within that band. It also comes, though, at a cost of some concern about stability. And so with inductive degeneration here, if you look at the S12 of the device, as you're adding that 16, that 20, that 24 picohenries, the S12 starts to increase as well in the band of interest. And so that lends to a basic trade space in instability. We start to see our device becoming more conditionally stable as we're adding this inductive degeneration. There's very little impact, though, on how the S11 or S22 might behave under those conditions. On the other hand, capacitive neutralization is another way we can introduce feedback. And this would presumably be used in a differential amplifier, but there are ways to use neutralization in single-ended amplifiers as well. What this capacitive neutralization looks like, we have to zoom in a little bit more here. And so the green area on the left plot that shows Gmax with increasing amounts of negative capacitance between the gate and the drain is then zoomed in on the right and basically shows how when we increase from 10 femtofarads to 16 femtofarads to 22 femtofarads, we get increasing amounts of gain at a specific frequency, in this case at 140 gigahertz, relative to the case where we don't have capacitance, feedback capacitance. In this case, one of the things we see is there's less impact on the conditional, on the stability factor of the device, the mu factor stability, than we observed in the inductive degeneration. And so this may lend some people to think that this is better because, of course, the neutralization's helping to isolate the device, and so the reverse gain of the device remains relatively low with respect to inductive degeneration. But when we really look at this and we compare these two approaches, we see, unsurprisingly, that essentially if we compare them for the same K equals 1 factor, they're basically a wash. So on the left, we see the source degeneration of the inductor as a function of G max at K equals 1. And the appearance of this second peak is captured through the dashed line in that plot. And so even though the black solid line decreases as we increase the source degeneration, we get this second spike that's giving us higher gain. Now, what that ends up doing is when we look at the K equals 1 at, for instance, 140 gigahertz, that green line drawn horizontally for the frequency 140, and we drop down to the gain that we're going to get, you can see that spike is basically going to push us back to about 7 dB. On the left, or sorry, on the right-hand side, when you compare at 140 with capacitive neutralization, we end up still getting 7. And so one of the things we point out with this very, very simple model is we tend to expect that embedding networks will produce similar Gmaxes if the feedback is right at the edge of conditional stability. And so that's one of the general observations. It's probably true, and the question just becomes what embedding network is best. Another way to look at this is, well, if I have an inductive, a way to introduce inductive feedback in my process, that's probably going to be lower loss than, for instance, adding a negative capacitor. In some other cases, like in FETs, the opposite might be the case. When we looked at, for instance, adding inductive source degeneration in the GaN HEMT device, you can see on the upper left how this behaves relative to a baseline transistor model when we look at compression in the T3 process. So adding that ISD of about 8 picohenries increased our gain from 6 to 7 dB. Again, we're getting about another dB of gain. But it doesn't really impact the way the output power or the efficiency behave. And so when you look to the gain compression, once we get to the point that the device is compressing, the feedback is no longer that effective, essentially. And between the red curve and the black curve on the PAE plot to the right, you can see that the PAEs are very similar. Zooming in on this from the standpoint of load pull on the bottom right, you can see again the delivered power and the peak PAE really don't change dramatically. There is a small amount of change which probably comes from the modeling, but there isn't a big win going from the baseline to adding that source degeneration and seeing that improvement in the delivered power or the peak efficiency. So embedding networks, we don't expect them to also provide some magical higher PAE or higher power. This is just going to be a question of what's best in terms of matching to the transistor. And so that's the perspective we take on embedding networks. It's not a magical bullet to get something special from the transistor other than a way to simultaneously provide multiple performance constraints. So we ended up using inductive degeneration in HEMTs. This is an example of how we introduced it in a 4x37.5 micron HEMT. The baseline device is shown on the left compared to a laid out transistor with a single via. What we ended up doing was adding multiple vias to control that source inductance. So we have to live with the via. If we put 3 vias in parallel, one would expect that the inductance might drop. But there's also a consequence of this that there's a longer feed path between the source of the device and those extra vias. And so when we went to 4 vias, for instance, we had substantially more inductance than we might in the single via case, in spite of having more vias in parallel, because the vias have to be placed further from the source of the device. And so there's a little bit of modeling that goes into figuring out if you need a specific amount of inductance, for instance, 8 picohenries, how you would actually get that by arranging the vias on either side of the device. So we looked specifically at 1, 3, and 4 via devices. And then we went and measured these GaN HEMTs from the standpoint of S parameters and load pull. And of course, as we might expect, if we can add a little bit more source inductance, we can push out the K equals 1. We can see a little more gain at in certain frequency bands. In this case, from 60 to 70 gigahertz, you can see the 3 and the 4 via on the left hand plot are giving you a 4 dB more gain because you're shifting the curve to the right. In the case of the S21 and the S12, we also looked at how the 3 and the 4 via devices behaved, and there wasn't a substantial change except at higher frequency bands. And we expected that from our analysis of that simple 5-element model. We expected that the S12 at higher frequencies would be degraded relative to the 1 via device. And so a more comprehensive model shows decent agreement between what we'd expect from adding source degeneration and the actual S parameters. Where things get interesting, at least in this particular experiment, was when we started to look at the large signal behavior, the IV characteristics, and ultimately the load pull. And here things began to deviate. We did expect that the HEMTs would, the S21 behavior and the S12 behaviors from the last plots, but when we looked at the IV plot in this curve on the lower right, the 3 and the 4 via devices compared to the 1 via device have much higher drain current, much higher Imax relative to the one via device. And this is going to ultimately show up as higher power density. The GM was higher, between 6.5 and 19% higher than the 1 via device. And that higher GM is, of course, good if you're building power amplifiers and you're thinking about Gmax of the transistor. So this was a surprise in the IV characteristic when we're looking at 3 different samples. And we wanted to confirm that this IV characteristic actually translated to a millimeter wave measurement. And so we went and we did a load pull characterization of the transistor with the help of the Mishra group here at UCSB. We have a 94 gigahertz load pull system. And we found that source degeneration indeed increased the gain at higher compression. And so it might be useful here to start on the right and look at the gain curves for the 1 via, the 3 via, and the 4 via device. And that 3 and 4 via device clearly have higher gain at higher output power, but moreover, they have significantly higher power. So we in fact are seeing the higher Imax translate into an increased output power. And that increased output power also translates into higher PAE for the device structure. So the black, now let's move to the left plot. The black curve on the right, on the left goes from 24% PAE to something that's reaching 30% PAE. So there's a little bit of a mystery about what adding these extra vias is doing if, in theory, as I showed, going from 1 via to 4 vias shouldn't change the load pull characteristic. We expected the same delivered power, we expected the same PAE, but when we actually do the experiment, we see a substantial change in the power density. And so this is one example where there's something going on that might be requires some more understanding of the devices. We also looked at G-band measurements on these devices just to give a flavor of what happens at these higher frequency bands. This is a little above the 140 that we were interested in, but we measured the maximum gain there, comparing the 1, the 3 via, and the 4 via device. And we ended up finding at 150, for instance, the 1 via and the 3 via were more similar in their behavior than the 4 via device. They had around 5 to 6 dB of gain at 150, which is in line with our expectation of 7 dB maximum gain at 140. Looking at this with higher current densities on the right, the same drain source voltage, you'd expect that there's around there's a lower gain, but it's also comparable. So one of the thoughts is that, well, that extra via, that might influence us by providing a better thermal path. And so we went and did this experiment where we measured the temperature with an infrared camera on the device under these different conditions. This is a picture of the setup. We had to apply a black body around the transistor so that the infrared camera would pick up the most contrast. And you can see what we ended up doing was sweeping the dissipated power through the device and measuring the change in the camera temperature. In general, we found these were probably fairly consistent results. We're not seeing something that leaps out and says that it's explaining a 1.5 factor change in the I max. The 3-via device did operate a little cooler, but not much cooler than the 1 and the 2-via device in this picture. And to give you an idea of what this looks like with the background, these were 9 different measurements taken across 3 different device breakouts under 3 different current densities and voltages. And you can see the consistency in that peak temperature that we were recording. So there's some indication that using inductive source degeneration is useful from the measurement standpoint, but let's go generally now to an amplifier, a power amplifier, and consider how we might use these embedding networks and what this might say about circuit design. So we've added, we generally want to use embedding networks as part of a matching approach, where we don't just want to get gain matching to boost Gmax, as I showed earlier. We can get 3 dB, but we want to also find a way that we can simultaneously get load line matching to the transistor. So we want to evaluate an embedding network more generally to get a simultaneous load line and gain match. The approach we took here was to consider a general circuit that can be used for embedding, and that's a coupler, a 4-port coupler. And what we can think about doing is doing the embedding in multiple steps, in nesting the embeddings one after the other. So shown on the right-hand side, we took the idea of putting a transistor amplifier inside of a coupler, and then imagined, well, if I have one embedding network that can be used to unilateralize the device, for instance, then I can add a second embedding network which can provide gain boosting. And in that way, I might solve multiple constraints in matching, and then find a way to synthesize these embedding results into an actual circuit. So we'll punt that part of the problem down the line. The way you might think about this is doing a signal flow graph, but it's easy enough with ADS to come up with generalized constructions of what a transistor amplifier would look like. So we considered a pre-matched transistor. So the S parameters are shown on the lower left for that pre-matched transistor, and a generalized coupler with a coupling coefficient alpha, which can be complex. And we put these two together to understand the S parameters of the composite, the embedded S parameters SE. And by solving one problem after the other, one of the outcomes we recognized is a magical property of a coupler is when you nest a coupler within a coupler, it just generates to a single coupler with a composite coupling coefficient. In other words, when you solve for the alpha that you want for unilateralization and the alpha that you want for boosting, you can implement both of those embedding networks as a single coupler with a modified coupling coefficient, alpha t in this case. And the way that alpha t is chosen from your conclusions for the unilateralization and the gain boosting is shown there, this equation for alpha here. So at the end of the day, we have an embedded device with S parameters at the bottom that show you the relationship between the alpha U and the transistor's S parameters. And one way we thought about understanding, one way to think about the trade space of adding this alpha U is we plotted this as a function of the imaginary and real parts. I apologize, it says alpha t, it should say alpha u. The imaginary and the real parts of the alpha on a gain plane curve. If we have no feedback, if we have no coupling in the device, then alpha is 0 in the real and the imaginary axis. And so this is something that's in line with the Gmax we'd expect from the transistor when no feedback's introduced. But when we start to add the feedback, we move along. We can move along a gain axis, a gain plane contour. You can see the real part of that gain boosting SB12 over SB21. Moving along that red line, we can increase the gain. You're walking up this this gain contour to a higher and higher gain until we reach around 11, 12 dB, which is the point at which we're at the edge of the conditionally stable region. And so we can keep adding feedback, and we start to walk into a place where we have positive feedback that's conditionally stable, and ultimately we may hit a very high gain, but that might not be realizable from the standpoint of stability in an actual circuit. So this gives us an idea of the type of alpha we'd like to achieve with that particular HEMT. So we implemented this idea in a 140 gigahertz amplifier, but we did some twists on it. We embedded a two-stage amplifier within what we calculated from those equations to be a 12 dB coupler. You can see the circuit on the right here. There's also a third stage that's used as a buffer to provide some isolation, but also to increase the gain. So we have a buffer stage before the 12 dB coupler, but the real interesting work here is in the two stages following the coupler that are part of a feedback network. And the circuit on the left, the micro photograph on the right makes it clear where the coupler is. It's a rather brute force approach at a coupler. One might imagine doing something that's lumped element. But we wanted to explore this theory to understand whether it had positive implications. These were the large signal and small signal results from the amplifier. We had a little shift in the frequency from around 140 to 136 gigahertz, but you can see we measured a peak gain of around 21 dB, which corresponded to about 7 dB of gain per stage. But if we think about the buffer amplifier, which probably has a little lower gain, indicates probably a higher gain in the core amplifiers. The plot on the right shows how the measured and the simulated gain behave, the simulated gain compression look in this amplifier. And one of the interesting things here is how the embedding network behaves under large signal conditions, which we wanted to understand. We actually found the measured PAE to be a little bit higher, around 7% PAE relative to our simulated result, which is around 5 to 6%. At 133 gigahertz, at 137, there was higher gain from the device, but the PAE was a bit lower. And that's not unexpected because we're on the edge of these rapidly changing gain contours. So across a couple gigahertz of frequency, we can see a rapidly different matching condition. Some details on this are presented in this paper we had in the Journal of Microwaves, I think a couple of years ago now. But this was an interesting approach to implementing embedding. We also ended up using, and this is separate work, the 3-via device that we had measured from the load pole to see how that behaved at 140 gigahertz. Again, we chose the 3-via device, as you saw before, because we understood it to have a higher Imax and therefore higher power density. And so, this is a repeat of what we showed before, but that 3-via device should provide some degeneration at 140 gigahertz, which is going to peak the mag. We did measure devices. We didn't see a big impact here, to be fair, when we measured these devices at 140 relative to the simulation. But needless to say, the power density arguments were still compelling. In a schematic here, we made a differential amplifier. In this case, there's balins at the input and balins at the output to separate this into two paths where we have two stages of gain in each of those differential amplifiers with an interstage matching network. This was designed to reach around 10 dB of gain. The balins do introduce significant loss in this process at 140 gigahertz. About as you can see, 1.5 dB of loss at the input and 1.2 at the output, which indicate why some of the back end of the line considerations are important when you're looking at matching. The results here gave us something in line with our gain under small signal conditions. We ended up measuring a bit better PAE. This reached about 8%. Again, the higher power density is helpful because we expected with the differential device to get around 22 dBm, 21 to 22 dBm per side. We got a total combined power of 23.5 dBm under this maximum PSAT. So again, the use of that inductive degeneration seemed to be useful for improving the output power from this process, and you can see the large area that those vias occupied in the actual amplifier core. So finally, I'd like to take a turn in the last section. One of the struggles that we found in using embedding networks is how accurately we can model transistors' behavior at high frequencies. It's obviously a hard place to do measurements directly of transistors. And I don't think that problem is going to get easier as people look to 200 gigahertz and beyond. Transistor modeling is a significant, let's say, productivity barrier to developing first pass success for mimics at these frequency bands. It takes years to get something that you're comfortable with. So one of the things we started to look at, a student of mine, Andrea Arias, who's now at HRL, started to consider, how do I do device modeling based on a lower frequency PDK model, and use that to influence or to predict better transistor parameters at higher frequencies where I might not have direct measurement. So this ANN modeling approach is really the first step that one might imagine in more ML and automation approaches and power amplifiers. We simply wanted to help improve our ability to prototype rapidly by using a neural network to improve the device model at 140 gigahertz. It could also be used for technology benchmarking, looking at emerging device technologies without necessarily going through the work of building mimics. So using a neural network model could help us figure out what process knobs will help improve the device without going and making a mimic. But we also were interested in, and I'm not talking about this work as much today, in how ML techniques could help optimize matching networks, combiners, and then even work with layout of devices to make as compact an implementation as possible, since that's going to be an important feature of future 6G technologies that might be based on arrays. So here's an example of the difference between a modeled and a measured transistor between 110 and 170 gigahertz. On the left, we see on the Smith chart, we've scaled the S parameters, and you can see the deviation in S21 as you get to higher frequencies, S22 as well as S11. And there's a bit of a rotation in S12 with respect to the transistor model on the solid lines. This might not be considered terribly bad for a 3.5 process, but if we're going to use these gain boosting techniques, you really have to have an accurate model. On the right, of course, we have the large signal behavior, which we already know it didn't produce the best accuracy for the single via device. And so we wanted to also see if we could help improve some of that large signal behavior from a neural network model. So the approach here for this was to try to learn an ASM HEMT model parameters using certain device measurements at different bias levels. So we measured S parameters at under different bias conditions, and de-embedded the extrinsic capacitances and model components, and then used those to generate training sets based on the model parameters, and used that to train the neural network. We looked at different types of neural networks in terms of the depth of the neural network, the number of nodes, number of hidden nodes, the type of activation function, and then train this using measurements from 8 different IVs and 7 different frequency steps. So we had 56 different outputs from the neural network to kind of come up with better model parameters. We were able to get some load pull access thanks to focused microwave. So we were able to get some input based on load pull, and we used this in later work on indium phosphide HBTs to help determine what the best load line conditions were. So when you can get access to a load pull, this could also be part of the model development using a neural network. But at first, we started out developing this around the large signal and the IV characteristic and the S parameter characteristics of the devices. So, I'm a little over time, but, we looked at power measurements again across different devices. As we got more interested in these modeling, we moved beyond just making transistor cells, but adding pre-matches. So the 3 variants here are a little different than what I showed you before, in that we added pre-matches that would help us load pull the devices at higher frequency bands and give us better agreement. But of course, once you're adding pre-matches, you're adding more uncertainty about what might be the device might be doing at under higher VisWAR conditions. This is what our ANN ended up looking like for the ASM HEMT. So our outputs here for the ASM HEMT show several different model parameters. The ones that are highlighted here were most important. We found most important to improving the S parameter matches. From the measurements that we did, we have the bias conditions and then the different S parameter magnitude and phase. We broke those out in terms of magnitude and phase rather than complex functions because that we found to improve the accuracy in terms of RMS error for the neural network. And in the parameter variants, you can see these are some of the S parameters that result when you start to train the model with these different parameters. And this is just a sample of different subgroups with different bias conditions that can sweep over large numbers of points and see the resulting S parameters very rapidly. This all can be trained within minutes, and I'm highlighting that because we wanted to look at lots of different training and validation sets. And so the details of these different training sets are in a later paper we've published this year, actually in January, that show the different types of activation functions and the number of outputs. And what we found as we went to larger numbers of hidden nodes, that we could get better RMS error in the S parameters. So the validation here was compared to the measurements of the devices, and just highlighting the comparison between our training and our validation. You can see the errors get below 0.1%, which we imagine is as good as it's going to be relative to the measurement certainty, the uncertainties in measurements of the devices at these frequencies. So at the end of the day, a comparison of our S parameters here shows what we ended up with in our neural network model relative to the PDK under different bias conditions. We thought this was an improvement. We got better than 5% RMS error under all different IV conditions, and we explore this in a paper that falls onto this RFIC paper that we presented last year that details the procedure for training and validating the neural network. So I'm a little over time, and I apologize for rushing the last part. The conclusion here, we think gallium nitride HEMTs are going to be extremely important for phased arrays, for beamformers that are developed above 100 gigahertz, And it's probably a matter of time when people will start to think about this commercially. In the meantime, there's a lot of interesting improvements in devices that will happen. I suspect we'll see better power densities. There's some work out of UCSB on N-polar, which is really pushing the frontier of power density towards, I think their numbers are close to 9 watts per millimeter. And that's certainly hopefully going to translate into power added efficiency. And as circuit designers, that's what I'm most interested in, is taking that device and getting the most power added efficiency. We explored embedding networks here, and I hope you have an appreciation for that topic. They're useful for gain boosting, but I think more generally, we'd like to see that field of embedding move towards multi constraint optimization, where we're getting high power density, high output power that matches the power density of the device, is not just gain boosting. And then finally, we introduced some ML techniques that we were looking at for using in our circuit design when we didn't have direct load pull. We had load pull, for instance, at 94 gigahertz, and we wanted to extract models that were at slightly higher frequencies. So in conclusion, I think the students who did most of the work here, Andrea is now at HRL, and I think still working on the T3 technology. HRL gave us access to this process. I appreciate that support, as well as the funding sponsors of this work, the SRC and DARPA under the JUMP programs, CommCenter and Cognizance. And finally, DARPA, through support of Tom Kasier on the LGAR program, and Focus Microwave for their help with load pull at 140 gigahertz. Thank you.